Previously, we have talked about double sideband suppressed carrier. Again, one of the simplest techniques of modulation, that is amplitude modulation. So therein we have a message signal m of t, and then we feed this message signal to the local oscillator, and after that we have a multiplier, and this signal is simply phi dsb-sc of t, right? And then we pass it through a channel, and we use the same oscillator at the receiver side. So coherent or synchronous demodulation. So this was modulation, and this is demodulation. In coherent or synchronous demodulation, we're using the same local carrier, and over here we'll get a signal which is phi dsb-sc of t multiplied by this carrier, which is cos 2 pi fct. So the multiplication of these two would yield a result which would include low frequencies and high frequencies, and eventually we would have a low pass filter, and at this point we will get back our original message signal in some form. Now the question is, uh, it is a very simple technique, so why do we need to look further? So the answer to that is there are some very serious limitations in double sideband suppressed carrier. So let us outline the limitations of double sideband suppressed carrier. So the first rationale is actually given over here, that you need exact local carrier at the receiver side. So this is a very big assumption. To consider that we have a broadcasting station. This is our AM broadcasting station that is transmitting a signal which is double sideband suppressed carrier, and we have a number of users, which is the actual scenario. So say this is our user 1, user 2, user 3, and so on, user n. So each user must have a local oscillator. So this is local oscillator 1, local oscillator 2, local oscillator 3, and up to local oscillator n. And each of this local oscillator must be synced with the local oscillator of the transmitter. So this is really quite a daunting task to create so many local oscillators, all of which are actually in sync with the transmitter local oscillator, right? So we need to look into a different kind of a model where we can simplify this situation. And what is that situation? That we need to make the user device as simple as possible. And again, by simple, we mean two things: simple in design, and it must be cost effective. So if we are having expensive devices and we are using them at the users, right? If users are buying expensive devices, we have number of users, so each one of them would be buying expensive devices. So the technology would become expensive. But at the same time, if we let all of these use simple and inexpensive devices, inexpensive but working devices, right? We can achieve this by changing the design of transmitter. If we change the transmitter, make the receiver simpler, so the life would be very easy. This is the main intention. In double sideband suppressed carrier, user is basically complicated. User needs an oscillator which is in exact sync with the transmitter oscillator. And we know that if the user is mobile, which is more often than not, so if the user is mobile, is moving, in that case, we would have frequency shift because of Doppler effect. Again, exact catching of the synchronization would be difficult. So therefore, we move towards a scheme in which we somehow modify the transmitter. And the way to do that is, again, we have the same modulator. This is the one that you have studied. So this is our double sideband suppressed carrier, dsb-sc. And after that, we include an addition block over here. And in that addition block, we feed this carrier. This feed forward link may have a gain of A, and then we forward it to the channel. So this is our phi amplitude modulated signal of T, phi AM of T. So the only thing that we have done right now is we have taken this carrier and also added it before transmission. So the transmission is over here. We may have an antenna over here. So this formulates what we call as AM, or you can also call it double sideband with large carrier. So let us look into what is a message signal, how this new block would affect the message signal in time domain and frequency domain, and what is actually happening in the amplitude modulation. So say we have a message signal. Let's say this is our message signal. Note that the only message signal is being multiplied with carrier, and this is something that we do in double sideband suppressed carrier. The new block is that we take the same carrier with gain A and add it to the modulated signal. This was previously the modulated signal, but this signal, which was I dsb-sc of T, now we add that with the carrier again, right? So we have A cos omega ct. So this is something that we have added with the original dsb-sc. So let us try to visualize again at each point, so that for the double sideband stress carriers, there's a revision for you as well. So say this is our message signal m of t, and it is slowly varying. This is the signal that we want to modulate. So this is modulating signal. Its Fourier transform, since it's a low frequency signal, so let us just say it has a Fourier transform which is m of f, which is over here, and it has a bandwidth of say bm. Again, we have a local carrier, which is this signal, and this is simply a cos function oscillating at a high frequency, and its Fourier transform is simply, we have two delta functions, one at plus fc, another one at minus fc. So next over here in this part, in the DSP, we were having this signal which is nice, and it is making an envelope, right? And this carrier is embedded in that envelope. Okay, so this was in time domain, and this is our phi dsb-sc coming from here, right? And its Fourier transform is simply, if these two are multiplied, then these two are convolved. So this would be convolved with this. So this is going to shift to fc. So at fc we have this part and this part, right? So we have m of f minus fc and m of f plus fc. Note that we are having 1 by 2 and 1 by 2 from here, because the strength of delta function is 1 by 2 for a cos function. So this is phi dsb-sc of f. Now coming back to this point, what is happening over here? So note that this was a signal. Let me rewrite it over here just to make it simple. That we have phi am of t, m of t cos omega ct plus this cos omega ct. We have set gain A equal to 1 in the second term. We can take cos omega ct common, so we would have cos omega ct m of t plus 1, right? So simply we are giving a DC offset of 1. This is what is happening based on this summation block. This means that we are giving this signal a DC offset of plus A, and we have set A equal to 1. So we're just giving a DC offset of plus 1. So hence we would have this translates to, say this was 1 at this block, now it would become 2. So we would have this format of pi am of t, and within this we have now, this is something that we have achieved from the block which is mentioned over here. But what is the benefit of it? Again, the benefit of it is, previously we were having a zero crossing, but we have set this signal in such a way that there is no zero crossing. This one is basically one literal, and you can what you call scale this. You can have something like m of t plus a, right? So this is more general form, cos omega ct. You can give a DC offset based on the amplitude of carrier, and this is the phenomena which actually helps us designing this application, which I have mentioned earlier, that we want to make the receiver of user simpler and inexpensive. So frequency domain is simply, we are having, this was dsb-sc plus we are adding this over here. That means we are adding two carriers. So if we add this signal with again two carriers coming from here, so we would have one over here and one over here. The dsb-sc, it didn't had any carrier, but phi am of f, this has this upper sideband, lower sideband plus carrier. So this carrier is basically added, and this is nothing but this is simply being added from this carrier cos 2 pi f ct. So we were discussing about the envelope E of t in AM, right? And herein we are saying that we are having an A plus M of t, right? So let me write again what is AM of t, and this is simply A plus M of t, and this is actually envelope. So within this there is the cos function here. We have cos omega ct. Let me say this is a coefficient. Let me write it as A or. Okay, so I'm saying this phi am of t is equal to A plus M of t cos omega ct from this block diagram, right? So let me write this whole coefficient as AR, and let me introduce another coefficient BR, and we can have a sine omega ct with it. So herein this BR is actually equal to 0. So that is why we get an AM. So basically this is whole 0. So when we are discussing the envelope, that is E of t, what we are saying is that we are simply having an A or square plus B or, that is the function in the in phase and in the quadrature phase, cos and sine, right? So eventually, since this is basically 0, so we are left with A or square, and this is simply A plus M of t. So this would yield A plus M of t, right? So the envelope is A plus M of t, right? So absolute value of it. So when it is useful and when it is not useful, it's a very important thing, because all of the things basically are governed by the envelope. So envelope is significant in AM. Now let us discuss the cases of envelope in AM. So the first case is, this is our case 1. Again we have a message signal which is something like this originally. So what we do is we give a DC offset, and this is represented over here. So whatever this value was, now it is basically, it is shifted upward. This is now A plus M of t. So now this is moved upward by A units. That is the DC offset. And since it is now moved upward, there is no point in this signal which is going below this 0, right? So that means a plus m of t is always greater than 0 for all values of t. And this is a very important statement. So when we have an envelope, the envelope will always be above the value of 0. So if it is always above the value of 0, so there is no 0 crossing. And if there is no 0 crossing, so this means that we can use envelope detector. And it is nothing but a very simple circuit that just needs one resistor, one capacitor, a low pass filter, and again one capacitor in series. So basically two capacitors, one resistor, and a low pass filter. So this is all that you need, and this is all that is basically available in the vehicles or in the radio devices that you have. So envelope detector is a very simple, inexpensive circuit, and we can demodulate the AM signal based on that. However, the cost that we have paid is that we have given a DC offset, which is A. What is a DC offset? DC offset is nothing but you are giving more power at the broadcast station. That means there is a broadcast station, you are powering it up. The message signal, previously you were sending m of t cos omega ct. Now you are multiplying a, you are basically giving a DC offset. That means the overall signal power would increase. So if the overall signal power is increased, that means you need more power to transmit the signal, right? Anyhow, this was the first case. Now let us look into the second case. So this is the second case, and we have not given a DC offset. We have not given enough power so that the message signal has gone above 0 for all values of t. So we have certain values which are still less than 0, right? And if we modulate this, we would have 0 crossing over here. And if we have 0 crossing, so we are at square 1, and we basically need coherent or synchronous demodulator. That is, we cannot use the envelope detector. And this thing is basically called over modulation. So if we have an over modulation, what we are actually going to do is we are again going back to the double sideband expressed carrier demodulator. So we need again a very expensive and sensitive receiver. In order for us to use AM as we use it today, we need the A to be such that we do not have 0 crossing in the envelope. Let us consider a case whereby we have a message signal which has a maximum value, and that maximum value is also equal to the minimum value. The simplest case is this sinusoid. So this is a single tone signal. It's basically a simple sinusoid, and it is having, let's say this is m of t. So this is our m max, that is the maximum value of it, and this is m min. So since it's a single tone, that means this is 0. So maximum value is equal to minimum value in the single tone. So this is our case. And we have already discussed that in order to modulate using AM, we need to shift it up. But the question is, how up is good enough? So the criterion to quantify that is basically the modulation index mu. Right? So we say that we have a modulation index mu, which is equal to the peak value of the message signal. Let me call it as MP. That is the peak value of the message signal. This is peak value of m of t divided by the offset that we're giving. So let us say we're giving an offset of AC or A or AC, whatever. This governs the modulation index. So we have now two cases here. Again, let us look into the first case, and let us repeat the message signal again, m of t. So the M of t right now is actually, you see there's an envelope. The low frequency signal would make an envelope, and this envelope in green is basically this thing. And within this envelope, we have high frequency carrier. But you can observe that this is basically oscillating up and down by unit a by 2. So this means that this is simply a by 2 and this is minus a by 2, right? So this is represented over here. And same goes for the lower block, right? So a by 2 is a peak value. So this means that our peak value for this signal, the green signal, is basically a by 2. Why? Because we are actually giving it offset of a. This is the DC offset that we're giving, right? So the peak value is a by 2 and the offset that we're giving is basically simply a. That mu is simply a by 2 by a, right? Uh, in this case, so this a would cancel with a, so our mu is simply 1 by 2. So basically we are having mu which is equal to 0.5 in case 1. So this also means that we are having a modulation of 50%. This is 50% modulated, right? And this is a plus a1 plus mu cos omega mt or omega ct, whatever. Can you address the second case? What is the peak value of this message signal? So herein we are giving a peak value of a, and that peak value is given an offset of a as well. So this mu is a by a. So in this case, the mu is simply a by a, which is 1, right? So this means that modulation index mu is equal to 1, right? So the second case, mu is 1. This means 100% modulation. So note that there is no zero crossing, right? But we are actually on the borderline. It's not over modulation, but we are on the borderline. We are just giving as much DC power or DC offset as required. Okay, so the case when we have a message signal in which the peak M max is not equal to M min. So we have a signal, say it message signal, which has a peak of value of say a maximum value of 1 and a minimum value of say minus 0.5. So in this case, the two peaks are not equivalent. So we cannot use this discussion that we have done, or this modulation index that is very simple and that we have done previously. So we need an alternate tool. So that alternate tool is basically represented over here, and it is actually not difficult. It's very simple. So again, we have modulation, right? So this means that we have made an envelope which is a plus m of t. So this is our envelope, and we find the global maxima, right? So the global maximum of this envelope is this point over here, and we multiply that by 2 to cover the whole range from positive to negative, and we term it as C, right? So we have a global maxima. So this is simply A plus M max. This was the maximum value, and we are giving a DC offset A. So this gives us the global maxima, and we are multiplying by 2 to cover both positive and negative values. The next thing is we are also finding the global minima. So we have a global minima also. Okay, global minima in our case is basically we're just looking at the envelope. So in the envelope, the global minima is this point within the envelope, right? So this is the global minima. Let me write it just to not make it confusing. So in this case, we have a plus the minimum value divided by 2. So we have this range. So we have now a modulation index mu for uneven kind of symmetries, and for that we use this C minus t and c plus d. If you just put in or plug in the values of c and d in this equation, so we'll have mx minus m min over 2a plus mx plus m min. So you may ask the question why we need this formula. So this is a matter of protocol. So for example, different regulators may use this as the criterion or the performance metric. Let us call it as key performance indicator, KPI, for the network. So you need the modulation to showcase it to some regulator, and that regulator goes with this definition of modulation index for the uneven symmetrical signals. In that case, you are following this definition, but there are other definitions as well, and different regulators follow those as well. So sometimes you would find a u plus and a mu minus, which is also representing these uneven y-axis shapes. So, but anyways, we'll be focusing on this in the textbook and in the course. So when we are discussing about mu, which is the modulation index, how efficient is the system itself? We are giving a DC offset. So is the system efficient or inefficient? So this deals with the area or the concept which is generally referred to as AM power efficiency or eta. Say this is our broadcast station, broadcast transmitting station, or base transceiver station. So how much power do we actually need to give, and whether the amount of power that we are actually giving, is it wasteful or is it useful? So how efficient is our overall system? So this is basically a metric that we define, which is eta, and this deals with the useful power over the total power, right? Now dealing the AM signal, so we have a signal which is having a carrier and sidebands. So this was simply dsb-sc, right? And it carries information. On the other hand, this is carrier or reference. Say this is pilot used for reference again. So this is not sending any information. This is just assisting or helping demodulate signal. This part is carrying information, this part is not carrying information. But we are looking into the total power. So if we are looking into the total power, how can we find the total power of phi am of t? So the total power, let us denote it by phi pt. This is simply limit t tends to infinity 1 by t time period t, and then phi am of t whole square dt. This is a standard formulation of finding the total power of a given signal. So now we have phi am of t, which is represented in this expression. We can complete the square. So we would have the integration, and within that integration we would have ac square cos square mc omega ct plus ac m of t, one cos from here, another cos from here. So we have cos square omega ct plus m of t cos square omega ct dt, right? And all of this is basically reappearing over here. Now we have three different signals. Let me denote them by three different integrations. Let me call the first one as I1, the second one as I2, and third one as I3. And let us solve each one of them.
So the first integration that we have called as I1, this links with the power in carrier. The second I3 links with the power in the sidebands PS, and the in between term, this I2, this links with the power in both the carrier and sideband. And these three terms are coming by completing the square of this expression. Now let us analyze the first term, the second, and the third. So in the first term, that is I1, which is we have a limit t tends to infinity 1 by t over time period t ac square cos square omega ct dt. Now this cos square omega ct, this is simply 1 by 2 plus 1 by 2 cos 2 omega ct, and within this is simply a cos function operating at twice the fundamental frequency. So hence the upper lobe would cancel with the lower lobe and so on. So this term would be equal to 0 based on this integration. So eventually we simply have this ac square by 2 coming out of this integration. So therefore the power in carrier, so this is simply ac square by 2. Now let us talk about the second term, that is again we have an I2, and now we have AC m of t cos square omega ct dt, and again this cos square is 1 by 2 plus 1 by 2 cos 2 omega ct. So from this analogy we can say this cos function would be 0 and we would be left with an I2 that is simply a limit t tends to infinity 1 by t, this 1 by 2 times this AC, this is constant, so we can take it out of the integration, and integration over time period t m of t dt. So this is our I2, and we can also say this is power in the middle term, that is in the carrier and sideband together. So this is the outcome. Whereas I3, so this is simply the power in the sideband, which was limit t tends to infinity 1 by t integration over t m of t cos square omega ct. So we have m of t cos square omega ct dt. So again this is 1 by 2 plus 1 by 2 cos 2 omega ct, so this would yield 0. So eventually we have this limit t tends to infinity. Note that we have a square over here as well, so that is we have this square coming from squaring this device. We have 1 over t m square of t dt. So the power in sideband, note that we would also have a 2 over here, so this is 1 over 2t. So the power in sideband is simply 1 by 2, 2 is coming from here, and then all of this is simply the power in the message signal. So we have power in the sideband, power in the middle term, and power in the carrier. So overall efficiency for any given signal is simply the power in the sideband over sum of these three powers. Let us take a very simple case of single tone, and we are interested in finding the power efficiency of a single tone signal. So the single tone in hand is m of t, which is referred to over here, and it has a peak value of am, and the negative peak is at minus am. So again the power efficiency of this is power in the sideband over total power. So from our previous discussion we said that the power in the sideband is equal to 1 by 2 power in the message signal. So power in the sideband is 1 by 2 power of the message signal PM. So how to find the power of this signal? So we know that for any single tone signal, the power of that signal is simply the amplitude square divided by 2. So that is, you are having a function which is limit t tends to infinity 1 by t, then a m square, and then this function which is cos square omega ct. dt. So from here we have again 1 by 2 plus 1 by 2 cos 2 omega ct. So this 1 by 2 would be extracted out, while this would yield a result which is 0. So hence we have power of a message which is simply am square by 2. So all of this suggests that the power of sideband is am square by 4. Alternatively, we have also mentioned that the modulation index mu for a single tone even symmetry around y-axis. So this is simply the maximum value of message signal, that is am, divided by the amount of shift which we can call as AC. And from here we can say that am is simply equal to mu AC. So we can say that the power of sideband is mu square AC square by 4. So this is our power of the sideband. Now what about the total power? So first let us say what is the power in carrier PC. We have already found the power in carrier, which is simply AC square by 2. So PC is AC square by 2, and then we have the power in the middle term. So let me rewrite over here again, that is we have PCS, which is limit t tends to infinity 1 by t m of t dt. But note that this m of t in our present case, again the upper lobe would cancel with the lower lobe, so all of this would yield a result 0. So this means that the middle term, that is PCS, which I have also mentioned as I2, this would simply be 0. So noting all of this, so this means that eta is power of the sideband, which is over here, that is mu square AC square by 4 divided by the total power, and the total power deals with power in the carrier, that is now AC square by 2 plus the combined power of carrier and sideband, that is 0, so it would not yield anything, plus the power in the sideband. So the power of sideband is also included in the total power. So we have again mu square AC square by 4. Now if we multiply and divide by 4, so we would have mu square AC square over 2AC square plus mu square AC square. Now herein we can cut off this AC square, so we would be left with mu square over 2 plus mu square. So this is the power efficiency of a single tone. Note that this result is only valid for single tone, because we can make this term equal to 0 only in single tone. But if it is not the case, then maybe there will be some value which would be appearing, and we have to cater for that. So what does this expression mean? So let us visualize this result over here. So we have power efficiency of a single tone, which is simply mu square over 2 plus mu square, and mu is the modulation index, that is the amount of offset that we give to the message signal. So for example, if we set mu equal to 1, so the single tone would have a behavior like this. So this is the case of 100% modulation, that is the borderline case, and this is the minimum amount of shift that we can give, and it would not have any zero crossing. So that is minimum DC offset that avoids the zero crossing, and this is simply mu equal to 1. So setting mu equal to 1 in the power efficiency expression, so we have 1 over 2 plus 1, so this is 1 by 3 So that is 33% efficiency or 0.33. So at best we can get this much efficiency only. And in fact, in most systems where the modulation is less than 1, which is more realistic, that is, we are having something like this. So this may be equivalent to mu equal to 0.5. So in that case, the efficiency would be even lower. So at best, when mu is equal to 1, so we have 1 by 3 efficiency, power efficiency. That is, 1 by third amount of power is consumed in the sideband of the total power. Now if you follow this curve, this case would be somewhere over here. This is 0.5. So we would be having even less efficient systems at lower modulation indexes. Now in this region where the power efficiency is 1, so this is the case where we have the double sideband suppressed carrier. That is, we are not having, or we are not transmitting any power in the carrier, right? So we are in this region. Now let us conclude the discussion by discussing some of the broadcast standards of AM, right? And in most countries, the AM frequency starts from 540 kilohertz and it is up to 1600 kilohertz, and with an increment of 10 kilohertz. So this 10 kilohertz means that the bandwidth of a given station is actually 10 kilohertz. One station is roughly having 10 kilohertz of spectrum. So within this 10 kilohertz you would have some god band, so actual bandwidth would be a little less. So we have a channel bandwidth of 10 kilohertz. Then carrier frequency stability is set to be plus minus 20 hertz, so it can be detected until then. The percentage modulation is 85 to 95%. That is, this is 100% and this is 95, 85 or 95% somehow. And we are setting different power strengths at different frequencies in this band for AM. Then we have harmonic distortion and the maximum transmit power that we can transmit at the base station. So in a nutshell, AM versus double sideband suppressed carrier. Assume that we have a massive signal m of t and the bandwidth of this massive signal is Bm. So the overall bandwidth of double sideband suppressed carrier is 2 Bm and that of the large carrier is again 2 Bm, because the only difference between the two is in one you have a carrier and in another one you do not have a carrier. So the overall bandwidth remains the same, that is 2 Bm. So carrier at the transmission, so we do have this carrier available in AM and in dsb-sc we don't have that, but on the receiver side we do not need a local oscillator. That is, on the demodulation side we can use an envelope detector, or we can also use a coherent demodulation for AM. On the other side, that is double sideband suppressed carrier, we do need coherent demodulation because otherwise we would not be able to track the zero crossing. And power efficiency is 100% for double sideband suppressed carrier because there is no carrier, whereas in AM the maximum that we can achieve is actually 33% for a single tone. So following were the references that we have used in the construction of this video.
The construct of AM modulators and AM demodulators is given in this video.